numbers. So we mentioned that to establish the connection, we need a socket, and part of the socket is the port number. So this port number is like a doorway that allows us to connect to a particular computer. It's like an open door that we could go through to establish connection to a particular machine. We have a bunch of ports on each machine. Each machine has many ports. Some of these ports are reserved for standard services. So they have a number. So the ports that are from 0 to 1000 are called well-known ports, and they are reserved for standard services. So for example, ports number 20 and 21 are used for the file transfer protocol. So when we are uploading and downloading files to a file server, and when we want to connect to the file server, we use these port numbers for our connection to the server. For SSH, remote login, we use port 22. For the simple mail transfer protocol, 25. So if we want to connect to the email server to obtain our emails, we would connect on this port. If we want to request a web page from a web server, we would establish connection on port 80. That was used for the hypertext transfer protocol. For the secure browsing, we have another port, 443, and so we have ports that are from 0 to 1000 are reserved for these services, and they don't change. The ports from 1000 to 5000 are changing. They are different every time. Whichever ones are available. These are used for the clients. So this socket happens both on the client side and on the server side. On the server, we get these well-known ports, but the client can pick up any number port which it has available from 1000 to 5000. Another thing in order to obtain the TCP service, we create these ports or sockets using the port numbers, and these are called endpoints. So once we create these sockets and we establish a connection between the client and the server, we can send data. So these ports from 1024 actually to 5000 are reserved for the clients. And so the data, the way we handle this data, in this layer, we have two main protocols. The first one is called the Transmission Control Protocol, which is what we have been talking about. And the second one is called the User Datagram Protocol. congestion control is handled by the transmission control protocol. The user datagram protocol is a very simple protocol that pretty much has the ports, the endpoints, and the sender and receiver, and does not implement any connections. This is used in some specific cases that we don't actually need connections, such as junk mail and things like that, or one request, one response. Let's say a query to a database server that we don't actually need to establish a connection, because a connection takes time, it's slow, and it adds overhead to the network. So there are certain applications that don't need it, and for them we get the user datagram protocol, but for the most of them that actually need it, most of the work is done by this transmission control protocol. Now, this protocol, the way it works is that if the message is too big, it might split it into pieces, which is okay, because if we have a sequence for each piece, and we know if it's the first, the second, or the last piece, and we can put them back together on the receiving side. But depending on the buffer space that we have, this protocol, TCP, can decide to split the message into many pieces, or it can decide to combine 2 or 3 messages together. It does not preserve the message boundaries. So it picks up data units from the application layer, and if it has enough space in the buffer, it might combine pieces of different applications together. Or it might combine different pieces of data together. Or it might split up one logical message into many pieces. So it does this at its own discretion. So for example, if the sending process does 512 byte writes to the TCP stream, this data might be delivered in the same way to the receiver, or they could be 2 pieces by 1024 bytes, or one 2048 byte piece. Like that. This is how the header looks like. Every byte on this connection that we've been talking about has a 32-bit sequence number. So the sequence number and all these port numbers and all these things that we've been talking about and the acknowledgements, all of the information is recorded in the header. So this is what the TCP header looks like. So this header that we added here, header port, this is the TCP header. It is very similar to the IP header that we've been looking at. It's a header, so it contains some control information. In particular, the port number for the sending machine, the port number for the receiving machine, sequence number. This is the number X that we have seen there. You know, the sending machine picked up a random number. It's a 32-bit number, and it's recorded in the header. The receiving machine acknowledged it. So we can send a whole segment just with that acknowledgement in there. The acknowledgement contains the next sequence number expected. So if this is X, then this will be X plus 1. And then there's a bunch of other information here. The length of the header, grayed out is unused bits. We have some bits here that are used for congestion detection and control. This is urgent data pointer. Okay. All of these bits, this is a single bit. It's either a 0 or 1. If the bit is set, then we have acknowledgement. If it's not set, we don't. This is push data, this is reset the connection, synchronize and finish. All these bits are used during the connection establishment. Window size, this will tell how much buffer space we have. If we don't have enough buffer, this will tell the sending machine to stop sending stuff until we free up the buffer because we don't have anywhere to put it anymore. Then this field is used for error detection, urgent pointer, and some optional fields, and after that the data starts. So this is what, once we attach this header to the message, it's called a segment, and it can be used by the transport layer by the TCP protocol. One of the things that this layer does, it handles congestion. What do we mean by congestion? I just said that we have a window size there, which will tell if our buffer is full, that the sender should not continue to swamp us with data because we cannot handle it. Can you think of a situation where this could happen? See, this is what is happening. We have a small capacity receiver, the bucket is full, and we have a high bandwidth network transmission that keeps dumping a lot of data on us, more than we can handle. Can you think of an example of something like that? This is the one situation. Okay, how about our cell phone? Our cell phone is a small device with about a small battery, with a small CPU on it, with a small memory, right? So if it's connected to some huge data center like Google, and Google is blasting stuff at us with the speed of the light on a small cell phone, then it can happen that it's blasting too much data at a too high speeds that our phone cannot handle it at that rate. So if that happens, that's the problem with TCP. That's the problem with the transport layer, and it's going to detect that. And it's going to say, my buffer is full, stop sending me stuff until I tell you that I have my application has processed the data, removed it from my buffer, and I have more space for you to continue to send the stuff, the data to you. Another situation is it's exactly the opposite situation. We don't have a problem with the buffer. We have a big bucket. We have a lot of space. We probably have some fast processing speeds, but the network has a congestion. So we have this bottleneck here, and it is slowing down the speed. And we're sitting there, and we're like, I want to watch this video, but the connection is too slow and the video is not loading for me, and I'm sitting here and waiting. That's when the network has a congestion. And we have different algorithms to deal with that, which are happening in this data, in the transport hub. One of the simplest ideas is to not inject new packets into the network until the old packet has been delivered. And the TCP manages this by adjusting its window size. So it uses multiple timers that it can solve this. So when a segment is sent, the retransmission timer is started. If the segment is acknowledged before the timer expires, the timer is stopped. If the timer goes off before the acknowledgement comes, the segment is retransmitted. Let's look at the UDP. So we mentioned that that protocol does not need a connection, does not use a connection for applications that don't need it. So if we don't want to have the connection, we have the option to go with user datagram protocol. And it's very simple. It takes the IP packets and just puts a little bit more information on top of them, such as the sending port and the receiving port. And that's pretty much all that it has in the header, and then the length of the header and some error check, and that's it. So this protocol can be used, like I said, for one request, one response, such as database applications or junk email. We don't care if junk email was delivered or not. If most of it makes it good, if not, then that's okay. Or if we are streaming videos and we want to implement our own connection to handle video streaming, we could take this protocol and write our own code to handle the video streaming. Okay, so this is all for the transfer layer. And now we're going to do something else. You can stop it.